So in the previous video, I was just explaining measurement uncertainty, and there was one open thing, namely, we had this situation where we had a source that produces values x, and another one that produces some other values, call them y now, and we compare these, and it's a comparison of distribution. So this delta was supposed to mean compare distributions. So I owe you an explanation now of how to do that. So you could, in this general statistical framework, you could think of a source producing classical outputs now. We don't care about the quantum inner workings of that, right? So this is a probability measure, and this is another probability measures. These are my standard letters that I use for probability measures. So these are two probability measures. And so I actually want to define something like a distance of these measures. Right? And this is now in a very general context. Remember I explained that this whole scheme can be applied to arbitrary observables, and the outcome sets there can be anything. They can be real numbers, they can be vectors, they can be apple, plum, and pear, or some kind of plus, minus, or whatever, some set, right? And so in order to find that kind of distance, we have to have an idea of how different individual outcomes are. So this starts from a metric on outcome set x, right? Let me write this as a capital X, and I do these two bars. And the metric is called D. And so it says that D of x and y is the distance of outcomes. Mind you now, not distributions, but just the outcomes. Yeah? So the example for that would be the outcome set could be the real number, and D of x and y is just the absolute value of the difference. Right? So this is a standard distance that you use. So implicitly, maybe we've been using this, but I just want to point out that if you want to do this in a more abstract, more general setting, you cannot talk about this kind of distance of probability distributions before you talk about the distance of outcomes. So we need some notion of that. Right? So, and okay. So then how different are two probability measures? What we actually know is that we want to have that if we have the distance of 2 point measures, I'll explain that in a second. These are delta functions, that's x and y, or delta point measures, they are called. That should be just the good old distance. And now delta x is the probability measure. It's called a point measure, which is the distribution that gives x with certainty. Right? So that describes a source that just says x, 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 right? Always the same value. And now the distance of these distributions is supposed to be just the distance of the points, right? Now the next thing we can do is we look at one of these point measures and another probability distribution. So delta of that would be the distance from such a point measure to a general probability measure. Now, this would be, you could take that, that's a plausible thing to do, right? So think of these measurements. One produces always x, and the other produces a distribution. And you want to say, how different are these two? Well, you want to quantify how far the y values are from x. And the only reasonable thing you can do at this point is to take the average. That is, you're integrating with respect to the probability measure uh, the metric. So this is the average distance from X. Okay. So, and of course, you can do the same the other way around. Metrics, by definition, are symmetric functions. So, uh, at the same time, you define the distance the other way around, right? So, distance of mu nu is always the distance of mu mu. So it's all that goes without saying, so to speak. So the tricky thing is how to define it when both are diffuse measures, right? That are proper distributions and not always the same point. Okay, so we just defined the distance of general probability measure from a point measure, as the average distance, which is the integral with respect to that probability measure. So d here is the typical integration d letter. This d is, of course, the metric. So we're just averaging the distances from the point with respect to that probability measure. That's an expectation value, right? And now I want to add one more structure here because that allows us to make better contact with the usual notions of statistics. So you probably have heard of mean square errors or something like that, or root mean square quantities. So that's what we're going to do here. So instead of averaging the distance, we average the distance squared, let's say. And we allow this exponent that I call the error exponent to be more general. It could be anything you like, right? So anything larger than 1, let's say. And so then the quantity we have here, that if alpha is a square, you would call the variance, right? If the distance is just a distance of real numbers. This is the variance, but that would then naturally come out in square meters. So if the distance is measured in meters, this is going to be square meters. And if we want to compare distances, it's sometimes nice to go back to the old units. So in order to do that, we take the root, right? And so here we take 1 over alpha. And that gives a quantity that depends on alpha, but it's the same sort of thing. It's like a mean distance with or the power of a distance. And actually, you could further generalize that to some cost function that you put here, but let's just do metrics for the moment. Okay, so the next step is a really interesting step. That is when we have two measures that are not point measures, then how do we say how far they are from each other? And so here, we go back to the work of Gaspard Monge. So distance of general measures. Is Gaspard Monge. Many people. That was rediscovered many times, sometimes called the Wasserstein distance, I don't know, Kantorowicz got a Nobel Prize in Kantorowicz, Kantorowicz got a Nobel Prize in economics for this, and I rediscovered it in my thesis, and so on. So many people have come up with this idea. But let's think of Gaspard Monge. And he was not just a French mathematician, but also a buyer, a builder of fortifications. So if you build a fortification, you find this situation. You have a heap of dirt. And what you want to do is a nice fortification. Something like that, right? So this is a fortress. And in my in this formalism, this would be the probability measure mu, or this given by a measure mu, and this is given by a measure mu. And now building it means that you pay the workers by meter and bucket. So if you have many workers that take this dirt and put it where it should go, and you have to pay them. And let's say the simplest pricing scheme, you pay them for every bucket they carry for 1 meter. And actually, the meter would be generalized to a meter to the alpha, right? So if they have to walk long distances, they get a bonus. They get paid by the square of the distance. So that's also a possibility. That would be the alpha here. So then the question is, so the distance of these two things is the minimal price that you would have to pay. So, of course, you can do this badly, right? You can make them run silly distances, like take everything from here to there and from there to there. That is costly, especially when you pay by meter squared, because there's unnecessary running that is involved here. So you need to find the optimal scheme, right? That is minimal here means for the optimal transportation plan, right? And we have to talk a little bit about what that means abstractly in terms of probability measures. What is a transportation plan? Okay, so for that I brought you a picture. So I brought you here the planning tool for the construction manager of that fortress building project. And I discretize it a little bit so you can see what's going on. And so in this scheme, the manager notices a little bucket symbol, right? There's this kind of thing. For every bucket that has been taken from A to B, and A, of course, would be the original dirt heap, B would be where it's supposed to go in the fortress. And the shading here explains the price. So if you have a long distance to travel, if you're far from the diagonal, you pay a lot. If it's very close, you don't pay anything. Right? So the shading here is the price, and you have to place the buckets in the right way. Now there's one condition. So the vertical here is where you take it from. So that is on this side, you would have the original dirt heap, right? So dirt heap. And here you have the fortress, right? And that just means that the buckets add up to where they have to be the total number of buckets that you need in every column to reproduce the corresponding piece of the fortress. So the condition here is that you have a distribution of buckets on this field in such a way that if you add them up in the right way, you get on the one side, first marginal would be the fortress, and the second marginal, that is the row sums, give you the dirty. Right? So that's the condition, uh, so that you're actually talking about the building project. And you are free to move these buckets around to optimize the price. So for example, if you have this kind of uh, thing in your construction tool, then you could move it to that, um, because if you do that somewhere in the picture, then the row sums and the column sums will both stay the same. So you keep satisfying your condition. So therefore, but the price might be different. So that depends on the shading in the background here, right? So you might actually save money by making this move. And now you can start playing or use computer optimization. And I could talk about that at some length, but this is the basic idea. This is the way you optimize, right? You make such moves, right? Okay, so then let us do the definition of what is known as the Wasserstein distance. So we say this planning tool in the language used by transportation metric theorists is, is called a coupling. mu and mu. So a coupling of these two probability measures is another probability measure. Let's call it gamma. And this is a measure on the Cartesian product, like this planning tool. And the condition is that the marginals are right? So that actually, if I take the expectation value, which is the integral over both these variables, of something that only depends on x, that is, I'm basically integrating out the y variable without any random variable to go with it, then this is going to be the integral. There's one given probability measure, that is the marginal relation, and also like gamma, let's say everything of x dy is mu of dy. Okay, so the marginals of this measure should be the given measures. Okay, let's go on then and define the distance. So now, in order to define the distance, we now take the average of the costs, right? So we say that the delta, depending on gamma, that's a delta-like quantity, depending on gamma, is now the average with respect to the coupling. And again, we do this thing, we allow this exponent alpha, right? Right. So if the workers are paid by the meter, it would be just alpha equal to 1, and if they're paid by the meter squared, then it would be alpha equal to 2. Right? So we take this thing, and then the distance of the two probability measures is defined as the minimum, say the infimum, the minimum of delta of y. This kind of depends on alpha. Let's put an alpha here. And let's take the root at this stage. This root here is needed to go back to square meters, but so this is the transport cost, basically at for the best transportation plan. Now this is what the minimum overall gamma. So that depends on gamma. So and the minimum of that function. It's not clear whether the infimum is actually attained always. I don't want to discuss that. So it could be an infimum, but the best lower bound on that is called the transport distance. Right? So this is okay. So let us apply this now, or maybe a few things to note. Right. So first of all, if one of them is a point measure, then there is not much you can do in your construction tool because all the buckets will be in the same row, let's say. So it's actually just the distribution of the output. So this formula reproduces what I defined before for point measures. Then let me just give you one other interesting feature here that will be needed for the uncertainty work. So if we are on R, right? So on what this the space X is the real numbers. Then one way two probability measures could be related is that one describes a source to which we add an independent noise source. Right? If we have a probability source that just so we have one noise source, and that just gets added to our signal, right? Then if the proper distribution of that guy is mu, and the distribution of the noise is nu, then this is the so-called convolution of the two, corresponding to the sum of independent random variables. So this is the sum, and the source and the noise are independent. So that's a way to mess up a probability distribution, right? And then the question is how far are these from each other? So this is the same distribution, but sort of smeared out with the noise. And then it's a very simple estimate to see that the delta now, the distance between the original probability distribution and the one that is messed up by the noise is, well, what is it? It should be the size of the noise. And actually, so this is the distance from zero of the noise. Right? And that's something that you can show in general, and actually simply by making a transport plan, by looking at this as a transport plan, as a coupling. Right? So we have a two-dimensional thing, and the addition is how they are combined. And then, so you can turn this into a transport plan, and this is the estimate that goes with it. Right? So adding noise makes a distance in probability, which is the size of the noise. Speaking of the size of the noise, this also comes up in the uncertainty work in another place. And let me just explain that. It's the connection with variances. So what is a variance? Or this is what we need in order to do preparation uncertainty. Right? So the delta quantities that describe what is the spread of the distribution. Right? And this is a similar notion, namely, so the variance measures distance from the nearest point measures. So actually, if I have a probability distribution mu, so let's say delta mu, this would be like the deviation of mu, right? That would be just the minimum, and in this case, the minimum would usually be attained, the minimum of the distance of mu from any point measure, right? And the minimum here is over x. So that is actually what we use as a distance of the spread. So example of this is, of course, your good old standard deviation, right? So that is if that we would have that alpha is equal to 2. We take quadratic deviations, and of course the space would be just r. Then the distance from a point measure was just this average, so that's the integral over the probability measure, or that should call that again. So of x minus y squared. And now we would minimize this over y. And that's actually how you should think about standard deviation. So that is the expectation value of y squared minus y squared. So this is like everybody's variance. Now we take the root of that. That is the 1 over alpha here, right? And we get the deviation quantity. Right? So the quantity that we need to describe preparation uncertainty, which is like for widths of distribution, is also one of these metric things. And that is why it's even possible, in the general case, to compare quantitatively preparation and and measurement uncertainties. Right? So they come from the same source. Once you've defined the metric, all these, and maybe given the error exponent alpha, you have a uniform set of quantities, a way to ascertain errors, to describe the size of errors, both for the measurement side and for the variance side. And so the only thing left to do, I think, is to define the distance between an observable and an approximate version of it. So this is supposed to be done done by comparison of distributions, but the distributions depend on the input state. So this is the maximum actually. So it's the maximum over all deltas of output distributions. And if you use this kind of delta quantity for the comparisons and measurement uncertainty, then the relation that I wrote becomes a theorem.